Good afternoon, all. Hope you all can hear me. Is that so? Can you hear me?
Yes, madam.
Yes, ma'am.
Yes, madam.
Okay, so under this course, Introduction to Probability and Statistics, right? So far we have learned 3 chapters, right? So the first one is about some basic theory behind the probabilities. What is a probability? Then some rules, additional multiplication rules, conditional probabilities, Bayes theorems, total probability theory. Likewise, we learned some basic concepts under the probability. And in the second chapter, we learned about the random variables, right? Random variables as discrete and continuous random variables. What are the random variables? Definitions, right? Then properties of random variables, those things we learned under the second chapter. And in the third chapter, we look at some specific distributions, discrete distributions, right? So under the random variables, we learned that there are 2 types of random variable, discrete and continuous random variables. And according to that, there are 2 sets of distributions, probability distributions, discrete distributions and continuous distributions. So under the chapter 3, we were discussing discrete special discrete probability distributions, right? So under that, so far we learned 6 distributions: uniform distribution, Bernoulli, binomial, geometric, negative binomial and hypergeometric distributions, right? There are 6 distributions we learned so far. So today, the final one, we're going to learn the Poisson distribution, right? So in earlier distributions, we learned some properties, we discussed example, practical uses, how to find mean, variance and moment generating functions, how to define probability distribution. Those things we learned under those discrete distributions. So today we are going to learn Poisson distribution, right? It is also a discrete distribution. In statistics, a Poisson distribution is a probability distribution that is used to show how many times an event is likely to occur over a specific period, right? So far in the discussed probability distributions, we didn't mention about a rate or a period or a space, right? Just the number, right? Just a number. But here we are discussing about specific period or a given space. In other words, it is count distribution. Poisson distributions are often used to understand independent event that occurs at a constant rate within a given interval of time. So here a rate is associated, the rate, right? A rate is associated. For an example, a number of telephone calls come in within a given day. So it describes about a rate within a day, or a number of printing mistakes in a given page of a book, right? Again, a rate of a space. Yeah, it's not related to time, it's related to a given space. But overall, it's talking about a rate or an average value, right? So those kind of scenarios are discussing under this Poisson distribution, right? So as in other distributions, it also has a definition. A random variable x has a Poisson distribution with lambda greater than 0 So as you can remember, in earlier distributions we discussed, there are some parameters that describing the distribution. Right? For an example, in binomial, we take the parameters n and the p, probability. N is number of events and p is the probability of success. Right? In hypergeometric also, there are some parameters which describe the distribution. So here, in the Poisson distribution, the parameter lambda is the parameter discussing the properties of Poisson distribution, lambda, right? Lambda. The random variable x has a Poisson distribution with lambda greater than 0, and it is referred to as a Poisson random variable if and only if its probability distribution is given by. So this is the Poisson distribution. Okay, so you have to recall this equation, the Poisson distribution equation, right? Wait a minute, my pen is not working. Okay, so this is the equation of Poisson distribution, right? Fx equal P, capital X equal X is e to the power minus lambda, lambda to the power x divided by factorial x for x equal 0, 1 up to infinity, right? So the notation is x Poisson lambda, right? So lambda is the parameter under the Poisson distribution. So here, as in other discrete distributions also, the distribution function fx satisfies the two properties, that is fx is greater than no, fx is greater than or equal to 0 for all x, and the summation of all of fx equals to 1, right? So we can prove it. So we take the summation of x goes 0 to infinity, the distribution, and we can take e to the power minus lambda out, and the summation of this part. So that is the definition of e to the power lambda, right? So we can write e to the power lambda as summation of all x lambda to the power x over factorial x, right? So that is the Poisson distribution, right? So as in other discrete distributions, we here also find mean, variance, and the moment generating function. So the expected value of x is the mean, and we can write it the summation of all x into the distribution e to the power minus lambda, lambda to the power x over factorial x. So e to the power minus lambda is not related to the summation, so we can take it out, e to the power lambda, and we can expand the rest as lambda plus 2 lambda squared over factorial 2. Likewise, we can expand the equation. Then we can take 1 lambda out, right? Then we can obtain e to the power minus lambda, lambda, and this expression. So this expression is the e to the power lambda, right? E to the power lambda. So it is the summation of all x lambda over lambda to the power x over x factorial, right? So we can write this is equals to e to the power lambda. So the mean of the Poisson distribution is the parameter itself, it is lambda, right? And talking about the variance, it is expected value of x squared minus expected value of x, the whole thing squared. So we write it as summation of all x squared into the distribution, and as in mean, we can take e to the power minus lambda out, and then we can write, we can expand the rest. We can expand the rest. And as in earlier, we can take lambda out. Then the inner part of the brackets becomes 1 plus 2 lambda plus likewise. And then within the bracket, we can again expand that, right? We can write it as 1 plus lambda like this. So this whole part, it is e to the power lambda, right? So then the rest, we can take 1 lambda out, and again this one is e to the power lambda. So we can take, right, or obtain the solution for e to the power x squared as lambda plus lambda squared. And by substituting it to the equation of variance x is e to the power x squared minus e to the power x the whole thing squared. Right? So variance is lambda plus lambda, sorry, e to the power x squared is lambda plus lambda squared, and expected value of x is expected value of x is lambda. So whole thing squared, lambda squared cancels out, and variance is also lambda. So that is an important property in the Poisson distribution. The parameter is lambda, the mean is also lambda, and the variance is also lambda, the same parameter. So that is an important property, right? So in the Poisson distribution, the mean and variance also equals to the lambda. Then we can obtain the moment generating function by obtaining the expected value of e to the power tx. So that is the summation of e to the power tx into the distribution. So as earlier, we can take e to the power minus lambda out and write it as etx lambda x over factorial x. Right? Then the part inside the summation, this one, right? So it can be recognized as a Maclaurin series of e to the power z, where z is lambda et, lambda e to the power t. So according to the Maclaurin series, the part inside the summation can be written as e to the power lambda et. Right? So finally, we can obtain the moment generating function as this. So I think you are going to learn this Maclaurin series under the mathematics courses. Right? So according to that Maclaurin series, we can obtain the moment generating function of this Poisson distribution. Right? Okay. So those are the properties or the features of the Poisson distribution. So in the Poisson distribution, we are talking about a rate, right? Rate, number of possibilities within given time interval or a space, right? The parameter is lambda. So we found mean, variance, and moment generating function. So now we are going to learn what are the uses of these Poisson distributions, right? So the Poisson distribution, there are two main practical uses of the Poisson distributions. So first read the second one as a model for the number of successes that can occur during a given time interval or a space. That is to consider the probability distribution of events that recur, such as telephone calls or typing errors. මම අර කලින් කිව්වා වගේ rate එකක් ගැන එයා තනියම distribution එකක් විදිහට serve කරන්න පුළුවන්. If we discussing about a rate, that is consider probability distribution events that recur, recur, such as telephone calls or typing errors within given time interval or a space, right? So that is one practical use, and rather than that, we are using this Poisson distribution as an approximation to the binomial distribution. As an approximation to the binomial distribution, right? In earlier distributions also, we discussed that some distributions can serve as an approximation to another distribution, right? So here we can use this Poisson distribution as an approximation to the binomial distribution, right? For some conditions, but under some conditions, right? So it is called as limiting form of the binomial distribution. So in place of binomial distribution, we can use this Poisson distributions under some limitations we learn now, right? So let's consider the first application or the first practical use, Poisson distribution as an approximation to the binomial distribution. How we can use this Poisson distribution as an approximation to the binomial, right? So when n is large, the calculation of binomial probabilities with the formula will involve a tedious amount of work, right? So let us see this example. Consider the calculation of probability that 18 of 3,000 students watching a parade on a hot day will suffer from heat exhaustion. So now n is 3,000, right? N is 3,000, a large number, not a small number, it's large, right? So what is the probability that one student suffer from heat exhaustion? So each and every student have the same probability, right? So it is 1 over 3,000. Probability is 1 over 3,000. So it is 0.005. Then what is the probability that 18 students within 3,000 students watching the parade will suffer from heat exhaustion? So X is 18. They are asking what is the probability that 18 students suffer from the heat exhaustion, right? So this is a binomial problem, right? A person or a student suffering from heat exhaustion is the probability of success. There are two probability, suffer from heat of exhaustion or not. So we take the success as suffer from heat exhaustion, right? Then the probability that a particular student suffers from heat exhaustion is 1 over 3,000, that is 0.005, right? 0.005. So it's 0.005. It should be 1.003. No. 1 over 3,000. 0.00S3 some. Right? So the probability value here is not correct. It should be somewhere 0.003, right? So just here let's consider, without considering P as 1 over 3,000, just as 0.005, right? Okay. They are given that probability that any student suffer from heat exhaustion is 0.005. Without considering that each student have same chance of being exhausted. Likewise, just we consider that probability that any student suffers from heat exhaustion as 0.005, right? Then according to the binomial distribution, as you can remember, it is n x, then p to the power x, and 1 minus p to the power n minus x, right? So when we substitute, the probability that 18 students will suffer from heat exhaustion can be written as 3018, 0.005 to the power 18, and 1 minus p is 0.995 to the power 2982. Right? So this calculation is very tedious. It's not very easy to calculate this one using a calculator also. So since n is a large number, we can approximate this problem into a Poisson distribution and make the calculations easier. Right? So now let us investigate the limiting form of the binomial distribution, and we will show that it becomes the Poisson distribution as n goes to infinity and p goes to 0 such that np equals lambda is a constant. So what are the conditions there? N is very large number, n goes to infinity, and p is very small number, such that np, the multiplication of n and p should be the lambda. It is the parameter we are using to approximate the binomial to Poisson. We know that there should be lambda to use the Poisson distribution. So we find lambda using n into p when n close to infinity or n is a large number and p is very small number. Right? So now we shall show that when n goes to infinity and p goes to 0, binomial distribution can approximate to a Poisson distribution. That means in place of binomial distribution, we can use Poisson distribution. Right? So consider this theorem. If x is binomial with parameters n and p, then for each value of x and p close to 0 with np equals lambda, that is a constant, the limit n goes to infinity. This is the binomial distribution. When limit n goes infinity, it can be approximated to a Poisson distribution. So this is the Poisson distribution. Right? So when n is large, p is small, and we can take np as a constant, that is lambda, then we can use Poisson distribution in place of binomial distribution. So we can prove that. First we start with the binomial distribution. Right? Then we expand this part ncx as factorial n divided by factorial x into the n minus x factorial, right? So we expand ncx there. Okay? We expand ncx. And then we take this lambda squared out and factorial x out here first, right? This part out, and then expand the factorial n, and the factorial n can be written as n into n minus 1 into n minus 2 up to n minus 6, right? So under that, the n to the power x is remaining and factorial n minus x. So these two cancels out. Okay. And we can expand this part as this, right? So here we know that P probability is So NP is lambda. So in place of P, we can use lambda over N, right? That is how this part comes. In place of P, we can take P as lambda over N. Then make these expansions. Okay. So this expression can be further expanded into this. Right? Then we can apply the limits. What happens when n goes to infinity? Okay. So this part remains as it is. And n goes to infinity. 1 over n, 2 over n. Since n is a large number, it closes to 0. And the remaining thing is 1, just the 1. Right? And then from the calculus, from the knowledge of mathematics, the limit n goes to infinity, 1 minus lambda n to the power n. This goes to e to the power minus lambda, and this part goes to 1. Right? So finally, it can be written as e to the power lambda to the power x over factorial x. So the Poisson distribution provides an approximation to the more complicated binomial distribution when n is large and p is small. So we can use Poisson distribution in place of binomial distribution when n is large and p is small, and the parameter, Poisson parameter, can be calculated using n into p. Right? So the next problem is, so any clarifications? Do you need any clarification? You can ask now. Okay, next question is, how large n should be and how small p should be? Right? So theoretically, it says when n goes to infinity. And practically, we are saying that n is large and p is small. Then how large it should be and how small p should be? That is a problem, right? So in many books, there are some approximation results they have used, but actually there is no any hard rule to follow how big it should be and how small it should be, right? In some books it says when n is greater than or equal to 20, some books it says 50, some books it says greater than 100, right? Likewise, there are some approximations, but we can say that the approximation gets better as n getting very large and p is getting p is close to 0. Right? So in your exams, normally we are saying that using this approximation, find this. Right? So there is no any hard rule. So you can take the decision how large n should be and how small p should be. Okay. Okay, let us discuss some examples and you will learn how to use this approximation. Okay. The first one, if 2% of the books bound at a certain bindery have defective bindings, Use the Poisson approximation to the binomial distribution to determine the probability that 5 of 400 books bound will have defective bindings. Right, so what is this distribution? 2% of books bound at a certain bindery have defective bindings. So that is the probability here. P is equal to 0.02. 2% is 0.02. Right? Use the Poisson approximation to the binomial to determine the probability. We have to find the probability that 5 of 400 books bound will have defective bindings. Out of 400 books, what is the probability that 5 books are defective bindings, right? So this is if we consider one book, it can be either a defective one or non-defective one. So the probability of success and failure, if it is a defective one, we consider it as a probability of success. Otherwise, it is a failure, right? So we have 400 trials. Why we have 400 books to check? So out of that 400, what is the probability that 5 books are defective ones? Right? So X, they are asking what is the probability that X equals 5. And here N is 400. So now we can see that P is a small number, 0.02 probability, and N is large, N is 400. Right? So if we use the binomial distribution for that, we can use this equation. 400 into 400C5, 0.02 to the power 5 and 0.98 to the power 395. So that is the binomial distribution if we find the probability, right? But since N is large and P is small, here we can use the approximation, Poisson approximation. So in order to do the Poisson approximation, we need the parameter of the Poisson distribution. So we can find it using NP. NP is equals to lambda. So 400 into lambda, 400 into probability 0.02, it is 8. Okay, it is 8. So now we can write the Poisson distribution. E to the power lambda to the power x over factorial x. So we need the probability that 5 defective books are there. X equals 5. E to the power minus 8, 8 to the power 5 and factorial 5. So using the calculator, it is very easier to find this. So this is the answer. So someone has asked me from email that to buy a calculator actually. So I don't know actually what are the current calculators or the latest ones, but don't waste too much of money. Actually, I don't know what are the current market prices as well. So it's better to ask from your senior or a colleague, right? මම ඇත්තටම දන්නේ නැහැ මේ මොනවාද තියෙන latest versions මොනවාද ඒවල price මම දන්නේ නැහැ. මොකද මම ළඟදී ගත්තේ නැහැ. ඒ ගැන දැනුවතුත් නැහැ. ඒක නිසා පොඩ්ඩක් මේ යාළුවන්ගෙනුත් අහලා ලොකු දේවල් තියෙන graphics අනම්මනම් තියෙන ඒවට යන්න අවශ්‍ය නැහැ. සාමාන්‍යයෙන් අපිට use කරන්න පුළුවන් ගණන් ලොකු ගණනක් නොවන එකක් ගන්නවා නම් හොඳයි. right? seniors ලගෙන් පොඩ්ඩක් ඒ ගැන අහන්න seniors ලගෙන් කලින් ඔයගොල්ලන්ගේ කසවර අරගෙන ඉන්නවා නම් එහෙම පොඩ්ඩක් අහලා එකක් ගන්න. right? එහෙම නැත්නම් seniors ලගෙන් ඉල්ල ගන්න උනත් පුළුවන් මොකද සමහරට ආයෙත් අවශ්‍ය වෙන්නේ නැහැ නේද? කවුරු හරි ඉන්නවා නම් නෑදෑයෝ හරි ළඟ ගෙදරක කවුරු හරි එහෙම ඉල්ල ගන්න මේ Tamanටම කියලා එකක් ළඟ තියාගන්න නම් හොඳයි. ඉතින් පාවිච්චි කරලා දෙන්න හරි එහෙම ගන්න ලොකු ගණන් වියදම් කරන්න එපා. graphics අනම්මනම් තියෙනවා එවනම් තීරණයක් නෑ ඉතින්. ඒක ලොකුවට ඕන වෙන්නේ නැහැ. scientific calculator එකක් ගන්න කොහොම හරි. right? okay. right. So what happens in actual practice? Can you remember in binomial also we used binomial table, cumulative binomial table, right? They have developed using computer software some table values, right? So we can directly easily calculate or easily find values, probability values using the table. So here also for the Poisson distribution, we hardly calculate Poisson probabilities by direct substitution in the formula. We often use tables of Poisson probabilities, either cumulative or exact, right, to obtain probability. So as in binomial Poisson distribution also, we are using probability tables, right? So in next page, you can see the Poisson probability values, right? Table values. So this is the cumulative Poisson probabilities, right? It's cumulative. So it does not give the exact probability value at an exact point, but it gives the cumulative values. That is probability where x less than or equals to r. R is the probability. Sorry, R is the point where we need the probability. For an example, so let's get an overview first. So this is the cumulative Poisson probability tables. So it gives the cumulative probability values, right? In columns, it gives the lambda values. These are the lambda values. 0.2, 0.4, 0.5, 6, likewise. Those are the lambda values. And in rows, it gives the R value, right? It gives the R value. So how we read this? So inside this, these are the probability values. If we consider this, right? So this is the probability where x is less than or equals to, value here is 3. Right? Probability x is less than or equal to 3, where x follows a Poisson distribution with lambda 0.6. It is equals to 0.9966. Right? So if we consider this value, what is that, this probability? So that is the probability where x is less than or equals to 6 for the where x follows Poisson distribution with the parameter 3.5. That is equals to 0.9347. Right? So that is how we read the Poisson distribution tables. Then here also for different lambda values and R values, the probability values are tabulated under the cumulative Poisson distribution tables. Okay. Okay, now let us see this example. This is an extract from the Poisson table where lambda is equals 2.4. So the random variable x follows Poisson distribution with the parameters 2.4. So find probability x less than or equals to 6. So it directly gives from the table, since it is the cumulative value. So it is this one, 0.9884. Right? Next one, probability where x greater than or equals to 3. Right? Greater than or equals to 3. So we can find it using 1 minus probability x less than or equals to 2. So that is same. So 1 minus 0.5697. See, it is 0.4303. Then the next probability x less than 8. X less than 8. So it's same as probability f x less than or equals to 7. That means x is equal to 7, x plus x equals to 6, x equals to 5, 4, 3, 2, 1, 0. All the probabilities we have to add. So it is 0.9967. Okay. Then probability x greater than 1. X greater than 1. So we can write it as 1 minus probability x less than or equals to 1. Right? So we can find it using the table 0.6916. Probability that x is exactly 4. It's equals to 4. So we can add up or get the cumulative value up to 4 and then subtract values, probability values up to p less than or equals 3. Then we can get the exact value. Right? So cumulative value up to 4 is this, up to this point, and the cumulative value up to 3 is up to this point. So if we subtract this one from this one, we can obtain the value where p x exactly equals 4. Okay. So it is same as in binomial distributions. In binomial tables also, we obtained the cumulative probability values. Here also, we are using cumulative probability values for the Poisson. Okay. Then we said that the first application is we can use the Poisson distribution as an approximation to the binomial distribution, right? So as in other distributions, the second practical use is Poisson distribution as a distribution of random events. Random events එකක් විදිහටත් Poisson distribution එක serve කරනවා. Right? Another useful application of the Poisson distribution is that it can serve as a model or a probability distribution to find number of success that occur during a given interval of time or space under certain assumptions. Right? The thing I discussed about the rate, right? For an example, telephone calls arriving at a switchboard during 1 hour. So it is discussing about number of telephone calls arriving at a switchboard during 1 hour. So it is the interval or interval of time we are talking about, 1 hour, within 1 hour period. Then number of car accidents at a particular intersection in 1 day. So during 1 day, number of accident occurs. The number of insurance claims made to a company in 1 month. So 1 month is the unit interval. And number of accidents in the factory in a week, a time interval. Right? So this is the given interval of time. Then what about the space? Number of typographical errors in a page. So it discussed about a space, not a time, a space. Page is the space. It is the unit interval. Then number of floors in 1,000 feet of wire. So not 1,000, 100. 100 feet of wire is the unit interval. Then bacteria in a given volume of culture. So given volume of culture is the unit interval. So overall, it's considered about average values, right? Average values within given time period or within space. Simply talking about a rate per typographical errors per page. Number of floors in number of floors per 100 feet of wire. Bacteria per given volume of culture. Number of telephone calls arriving at a switchboard per 1 hour. Right? It's discussing about the rate. So it can be within given interval of time or within given interval of space. So it is called as the given interval of time or the given interval of space is called as unit intervals. Okay. So the definition of Poisson distribution, let lambda be the mean number of occurrences of a recurring event in a given interval of time or space, and x denote the number of such events that occur in the given interval under the following assumptions. So Poisson distribution follows some assumptions, right? There are 3 major assumptions. The first one is the probability that an event will occur in a given short interval is proportional to the length of interval and does not depend on the position of the interval. So if we consider a short interval, right? For an example, consider number of telephone calls arriving at switchboard during 1 hour. If we consider 1 minute period. 1 minute period. So it is the probability is depend on that interval, right? But it does not depend on the position where it takes. අපි පළවෙනි විනාඩි 5 ගන්න එක දෙවෙනි විනාඩි 5 ගන්න එක එහෙම depend වෙන්නේ නැහැ. හැබැයි ඒක time interval එක මතයි depend වෙන්නේ. right? අපි විනාඩි 5ක් ඇතුළත එන calls වල probability එක විනාඩි 10ක් ගත්තොත් ඒ දෙක depend වෙන්නේ ඒගොල්ලෝගේ interval එක මත විතරයි. It does not depend on the position. අපි පළවෙනි විනාඩි 5 ගන්නවද දෙවෙනි විනාඩි 5 ගන්නවද නැත්නම් තුන්වෙනි විනාඩි 5 ගන්නවද කියන එක it doesn't matter. Depends on the interval. විනාඩි 5ද 10ද කියන එක මත depend වෙනවා. හැබැයි විනාඩි 5කට එන calls වලට වඩා විනාඩි 10කට එන probability එක වෙනස්. So it depends on the interval. Right? The probability does not depend on the position where it takes, but it depends on the length of the interval. Right? Then the second one is the occurrence of events in non-overlapping intervals are independent. Right? So occurrence of events in non-overlapping intervals. So if we consider first 5 minutes, it is independent from the previous 5 minutes. Second 5 minutes, the occurrence of second 5 minutes is independent from the first 5 minutes, since it is non-overlapping. So the occurrences of events are non-overlapping intervals. The occurrence of events in non-overlapping intervals are independent. The third one is the probability of 2 or more events in a short interval. If we consider delta t time interval, so the probability of 2 or more events is negligible. So those are the three main properties or the assumptions that Poisson distribution follows. Okay, so then next follows the Poisson distribution with parameter lambda, that is this equation. So this is the one we discussed earlier as well. So here unit interval means the given interval of time or space may be treated as the unit intervals. In this example, we discuss what is a unit interval is. Right? Okay. Corollary. What is a corollary? Actually, it's like a theorem, but it is it's not a main theorem. A result we obtain through a main theorem, it is called a corollary. So that is a corollary. If a random variable x is Poisson with lambda in a given interval, then the number of events that occurs in an interval of t unit follows the Poisson distribution with parameter lambda t. Right? If x follows the Poisson distribution with lambda for given interval, right? Then number of events that occurs in interval of t time units follows Poisson distribution lambda t. For an example, if number of accidents in a week follows Poisson distribution with lambda, then the number of accidents in 2 weeks follows the Poisson distribution with 2 lambda. Right? Then the number of accidents in a month follows, which contains 4 weeks. It is Poisson with 4 lambda. Then the number of accidents in a day, since a week has 7 days, it is Poisson distribution with lambda over 7. Right? So that is how we obtain Poisson distribution with several given intervals. Okay, any problems up to now? Okay, let us consider these examples, right? The average number of trucks arriving on any one day at a truck depot in a certain city is known to be 10. What is the probability that on a given day, fewer than 9 trucks arrive at the depot? Right? So, they are asking what is the probability that on a given day, fewer than 9 trucks arrive at depot. So, that means the random variable here we are considering is number of trucks arriving at the depot on a given day is the random variable. Right? So the average number of trucks arriving on any one day at a truck depot is 10. So this gives us a hint of lambda. So lambda is equals to 10. The average number, right? The average number. So it gives us a rate. Average number of trucks. So this X follows a Poisson distribution with lambda equals 10. Number of trucks arriving at the depot on given day follows a Poisson distribution with 10 lambda. Right? So now they are asking what is the probability that on a given day fewer than 9 trucks arrives at the depot. Probability that X less than 9. That means we need to find Px equals 0 plus Px equals 1 up to Px equals 8. So that is same as saying Px less than equals to 8, less than or equal to 8. So using the Poisson tables, you can directly find it. So the answer is 0.333. Okay, read the next problem 2, example 2. Okay, in this example, a book containing 500 pages has 750 misprints. Right? First, what is the average number of misprints per page? So we can find the average. 75 over 500, that is 1.5. Then find the probability that page 427 contains no misprints, exactly 4, more than the average number of misprints. Right? So this is a Poisson distribution. If we take the random variable as number of misprints per page, number of misprints per page. So we have found it, found the average number of misprints, average, the rate, එක page එක තියෙන misprints ගාන කීයද අපි හොයලා තියෙනවා. Right? So now, assuming the misprints occur at random, we can take x as the number of misprints. So it follows a Poisson distribution with the rate lambda 1.5. Okay. So according to the equation of Poisson distribution, we can write this. Px equals x. It is e to the power minus lambda, lambda to the power x over factorial x. So the first problem, no misprints. Find the probability that page 427 contains no misprints. So why it says page number 427? There are no any speciality. It's just a page. No any specialization. Since the misprints occur at random, විශේෂයෙන් කියලා 427 වෙනි පිටුවේ කියලා විශේෂ දෙයක් නැහැ. ඕනම පිටුවක් වගේම තමයි. Right? So Px equals 0 in any page. The probability that having no misprints, we can just substitute to the equation, or else we can use table values if it's available. So we can write it as e to the power 1 minus 1.5. Since x is 0, the answer is 0.223. Then exactly 4 misprints. Px equals 4. Then in place of x, we have to substitute 4. See here, 4. Then value is this one. And more than the average number of misprints. That means x greater than 1.5 is the average one. So it can write written as 1 minus Px less than or equals to 1.5. So the probability values where it less than 1.5 is x equals 0 and x equals 1. Then the answer is this one. Right? Then part C. Find the probability that pages 427 and 428 contains no misprints. Now again, there is no any speciality, but here now 2 pages, not per page, 2 pages. Find the probability that 2 pages contain no misprints. So we consider x as misprints per page. Now we want number of misprints in 2 pages. Right? So now we define a new random variable y, number of misprints on 2 pages. If it is a 1 page, per page, it follows the Poisson distribution with the parameter 1.5. If it is per 2 pages, so according to this corollary, events that occur in an interval of t unit follows Poisson distribution parameter lambda t. So here it should be per 2 pages, it should be a Poisson with 2 lambda, that is 3. So now find the probability that pages 427 and 428 contains no misprints, means y equals probability of y equals 0. So it's just e to the power minus 3, it is equal 0.05. So is it clear? Okay. Any problems up to now? Okay, next, move on to the next section. Diagrammatic representation of the Poisson distribution. So as in binomial distribution, we can represent the Poisson distribution using a diagram or the vertical line graph. The following vertical line graph shows the probability distribution X follows a Poisson with lambda for various values of lambda. The horizontal axis gives the values of X and the vertical axis gives the values of probability where X equals X. Notice that for small values of lambda, the distribution is very skewed, but it becomes more symmetrical as lambda increases. So here the vertical line graph, right? So this is X-axis. It gives the values of X, and here this is X, and here this is probability f of X equals X. For different values of lambda. See here, 1, 1.6, 2, 2.2, 3, 3.8, right? So you can see here, when the lambda is low value, it's very skewed. See the first graph, it's skewed, not symmetric, skewed, positive skewed, right? So when the lambda increases, it reduces the skewness. See here, it is close to symmetric. In this one, it's somewhat close to symmetric, not very much skewed. And here, can you see here? When Poisson becomes 10, it is a symmetric one. It's close to symmetric one. Right? So that is a special property of a Poisson distribution. When lambda increases, it becomes a symmetric distribution. When lambda is a low value, it is a skewed distribution. When lambda goes high, then it is a symmetric distribution. So for small values of lambda, distribution is very skewed. but it becomes more symmetrical as lambda increases. So that is the thing I wanted to point it out in this diagrammatic representation. Okay. So then the mode of the Poisson distribution. Mode is the value which is most likely to occur. So as we discussed in binomial distribution also, the one with highest probability. Okay. Okay, consider this graph again. So here, the highest probability occurs when x equals 0 and 1. See, same high probability. Okay, so in second one, lambda is equals to 1.6. There is one high probability. When lambda equals 2, again there are two probability values, two high probability values. Here x equals 1 and 2. Right? When 2.2, only 1. When it comes to 3, again two high probability values, 2 and 3. When x equals 2 and 3. Right? In here also, when x equals 5, two same probability values where x equals 4 and 5. In 10 also there are two values when x equals 9 and 10. So it is clear. We can notice that when lambda equals 1, there exists two modes where x equals 0 and 1. When lambda equals 2, again two modes, one where x equals 1 and 2. When lambda equals 3, again there exists two modes, 2 and 3. When 5, two modes, 4 and 5. When lambda 10, two modes, 9 and 10. Right? So we can see there is a special feature here. When lambda is an integer, there are two modes. If the parameter of the Poisson distribution is an integer, there are two mode values. What are those two mode values? The lambda minus 1 and lambda. Those are the two modes. They are having the highest probability. X equals lambda minus 1 venakotai, lambda venakotai. It reports the highest probability when lambda is an integer. Right? What happens when lambda is not an integer? So according to the graph, when lambda is 1.6, one mode. Right? Lambda is 2.2, again there is one mode. But in 1.6, the mode is 2. Here, sorry, 1. Right? When lambda is 2.2, one mode, x equals 2. Lambda is 3.8, one mode, x equals 3. So you can see here, when lambda is not an integer, if it is 1.6, mode is 1. If it is 2.2, mode is 2. If it is 3.8, mode is 3. So if lambda is not an integer, the mode occurs x equals m such that m is in between lambda minus 1 and lambda. right? So here lambda is 1.6. So mode is in between lambda minus 1 and lambda. Lambda minus 1 is 0.6 and lambda is 1.6. So it's in between those two values. So since the mode is x value is an integer in discrete case, it should be the integer value between that range. In between that range. Right? So if lambda is something 4.56, so definitely the mode should be 4. So that's how it occurs, right? So using the graphical representation, we obtain two main properties. When lambda is a small value, it's a skewed one. And when lambda increases, it becomes more symmetrical. And considering about the mode, if the lambda is an integer value, there are two modes. The two modes occur at x equals lambda minus 1 and x equals lambda. And when it is an integer value, the mode occurs at x equals m such that m is in between lambda minus 1 and lambda. Right? Any problem up to now? Okay. Right. The next one, fitting a theoretical distribution. Fitting a theoretical distribution. So in binomial distribution as well, we discussed this one, how to fit a theoretical distribution, right? So why we need a theoretical distribution? So if we have an experimental result, right? We have an experimental result and we want to find whether that experimental result or experiment follows a given distribution. Then we can build up a theoretical distribution using the experimental results and compare that experimental result with the theoretical results and check whether it follows the given distributions or not. So that is the purpose of finding theoretical distribution, right? So we have experimental result and using the experiment. So we want to find out whether that experiment follows a given distribution or not. So in this case, if we want to find whether the experimental result Poisson distribution or not. So we build up a theoretical distribution using the experimental result and compare the values of theoretical and experimental result to find whether the given experimental result follows the probability distribution under the distribution we build up the theoretical result, right? So here we only learn how to fit the theoretical distribution. The comparison part is done in higher levels, in level 2 or yes, level 2 or 3, yes, most probably in level 3, I guess, right? The chi-square distribution, right? Okay. So as with the binomial distribution, it is possible to fit the theoretical Poisson distribution to experimental data. Let us consider the following problem. The following table shows the number of employees injured in a week in a certain factory recorded over a period of 52 weeks. Right? So, the problem is here they are considering over 52 weeks. Within that 52 weeks, they are calculating or they are finding the number of employees injured in a particular week, in a week. Then they note down how many weeks are there where the number of employees injured in a week is equals to 0 or 1 or 2 or 3 and 4 or more. So out of 52 weeks, there are 31 weeks that no one is injured in that 31 weeks. සති 31 ඇතුළතම ඒ කියන්නේ අපි සති 52ක් consider කරනවා. So if we consider first week, අපි පළවෙනි week එක consider කරනවා. ඒතර ඒ week එක ඇතුළත accidents කීයක් වුණාද කියලා බලනවා. Right? අපි හිතමු ඒ week එක ඇතුළත accident උනේ නැහැ කියලා. එහෙනම් මෙතෙන්ට එකක් එකතු වෙනවා. දෙවෙනි week එකේදී accidents දෙකක් වුණා. එහෙනම් මෙතෙන්ට එකයි. තුන්වෙනි week එකේදී ආයෙත් නැහැ. මෙතෙන්ට එකයි. ඒ විදිහට බලලා අපි මේ calculate කරනවා. එක accident එකක්වත් උනේ නැති සති කීයද? accidents එකක් විතරක් වුණ සති කීයද? accidents දෙකක් විතරක් වුණ සති කීයද කියලා ඒ විදිහට count කරනවා. So this is the experimental result. Right? So x can take values 0 to 4 or more. Right? 0 to 4 or more. So give reasons why one might expect this distribution to approximate to Poisson distribution. ඇයි මේක Poisson distribution එකට approximate කරන්න කියලා reasonings අහන්න. Right? So this is a recurring event. Recurring event ආයෙත් සිදුවන්නේ හැම සතියක් පාසාම සිදුවන event එකක්. And the number of accidents in a given interval satisfied the assumptions under which a Poisson process takes place. Right? Further, the frequencies which may be assumed to be proportional to the respective probabilities are decreasing rapidly as in Poisson distribution for small value of lambda. Right? So, when x increase here, x increase, right? Respective probabilities are decreasing rapidly. So can you see it? Number of weeks having the number of accidents x is rapidly decreasing. So as you can remember here, see here, it rapidly decreases when lambda for a small value of lambda, right? So we might expect this distribution to follow a Poisson distribution. We can't exactly say that this follows a Poisson distribution, but we can expect this distribution follow a Poisson distribution because it follows the properties of a Poisson distribution, right? So that this is the way how we are writing the reasonings. Okay, so we can't say in this point we can't exactly say this is sure to be a Poisson because we didn't build up the theoretical distribution and compare it with some statistical results, but according to some properties we see this might be a Poisson distribution, right? So the second part, evaluate the mean and the variance of the data. So we have to obtain mean and the variance, right? So how we find the variance? So this is a frequency data. So we can just find mean as summation of fx over summation of f. 0 into 31, 1 into 17, 2 into 3, 3 into 1, and 4 into 0. So x bar is 0.5. The mean of the distribution is 0.5. Then the variance. So you know how to find the variance in the frequency table. In A-level class also we learned these equations. Under the statistics part, there is a section in your A-level mathematics, I guess. So the variance is found to be 0.5. Then see here now, sigma is also 0. Sigma squared is also 0.5. The mean and variance are equal. So as you can remember, in Poisson distribution, the mean and variance are equal. It is equals to lambda. Right? So we know that expected value of x equals to variance x for a Poisson distribution, and therefore the fact that x bar equals sigma squared gives further evidence in favor of the Poisson distribution. So another clue, we having another clue that this experimental result might follow a Poisson distribution. Right? Then part C, calculate the frequencies of the comparable Poisson distribution. Okay, now we are going to build up the theoretical distribution, right? Calculate the frequencies of the comparable Poisson distribution. So let us use the mean. So we know that lambda is 0.5 now. Mean of 0.5 as the parameter lambda of the Poisson distribution. And the random variable is the number of accidents in a week. X can take from 0, 1, 2 up to infinity. Here 4 and more, right? 4 and more, since we are considering 4 and more, we let the limit as infinity. Now we can calculate the probabilities for x equals 0, 1, 2 and obtain expected frequencies by multiplying them by 52. Right? Okay. So we are first finding the probability where P, number of accidents x equals 0. Right? Using the equation we can find it. We just substitute values. In place of x, we put 0. In place of x, we put 1, 2, 3 and 4. Then find the probabilities in 1 week. So here, this is the, so this one is the probability having no what is it defects? No. Injuries. No injuries. This is the probability within the week, within 1 week, no injuries. This is the probability within 1 week, there is only 1 injury. This is the probability within 1 week, there are 2 injuries. This is the probability within 1 week, 3 injuries. This is the probability 4 injuries. Right? So this is the probability within 1 week. But we need within 52 weeks. So we multiply this by 52. multiply this by 52. So this is the expected frequencies rounded to the nearest integer. Right? This is the expected frequencies. So the theoretical distribution is this one. So what is the experimental result? Here 31, 17, 3, 31, 17, 3, 1 and 0. So these are the experimental result. This is the expected frequency. So this theoretical distribution compares reasonably well with the original data. So it's somewhat similar here. See, here it is 32, 31, 16, 17, 4, 3, 1, 1, 0, 0. Right? So this is the theoretical distribution. So next steps is to use a statistical test to check whether this experimental result followed the theoretical results. So in order to do that, we use a chi-squared test. Chi-squared test used to compare the two sets of data. And using the chi-squared test, we can decide whether this experimental result follows the Poisson distribution with mean 0.5 or not. So we learn this chi-square test in higher orders, higher levels, right? So any problem up to now? Okay, then the last part, the distribution of two independent Poisson variables, right? The sum of two independent Poisson variables with parameter m and n respectively is a Poisson variable with parameter m plus n. Right? So if we have two Poisson distributions, the first one is Poisson distribution with parameter simple m, and second one with simple n. Then the summation of two variables, the summation of two variables follows a Poisson with the summation of m plus n. Right? So we can prove it. So since let's consider x is a Poisson with m and y is Poisson with n. So we can write x, the equation px equals x is e to the power minus m, m to the power x over factorial x, right? And then we expand it. When px equals 0, it's just e to the power minus m. X equals 1, e to the power minus m into m. And px equals 2, e to the power minus m squared over factorial 2. Likewise, we can write the Poisson with parameter n as well. Right? Now, we are considering the summation of two probabilities x plus y. Two random variables x plus y. Right? So let's find the probabilities where x plus y equals 0. x plus y. Now we are considering the random variable x plus y. Right? If someone wants, you can take x plus y as z. Right? So x plus y equals 0. So x plus y 0 when now both random variables should be 0. X also should be 0 and y also should be 0. So we are multiplying two probabilities since they are independent. So when x equals 0, it is e to the power m, e to the power minus m, and y equals 0, it is e to the power minus n. So it is e to the power minus m plus n. And the next one is the random variable x plus y equals 1. How it happens? Either x should be 0 and y should be 1, and x should be 1 and y should be 0. So we are just substituting. When x equals 0, it is e to the power minus m, and y equals 1, it's e to the power minus n into n. Plus, when x equals 1, e to the power minus m into m, and y equals 0, it is e to the power minus n. So, it is e to the power minus m plus n. We can take it out, and remaining part is n plus n. Right? Likewise, then we can write p x plus y equals to 2. There are three possibilities. X equals 0 and y 2. X equals 1 and both x and y are equals 1. And on x equals 2 and y equals 0. Right? So by substituting, you can obtain this one. Right? So if we write the probability distribution of x plus y, the random variable x plus y, we can write it as this. Right? So, in general, this can be written as probability x plus y equals x plus y, e to the power m plus n minus n plus n, then m plus n to the power x plus y over x plus y's factorial x plus y. So if we write x plus y equals 3 here, we can write it as e to the power minus m plus n into m plus n to the power 3 over factorial 3. So we can generalize it like this. So this is the Poisson distribution with m parameter m plus n. Right? So if we having two random variables x and y with the parameters m and n, then the sum of the two random variables x and y follows a Poisson distribution with m plus n. Okay. Now let's consider this example, final example. So two identical racing cars are being tested on a circuit, right? Two identical racing cars are being tested on a circuit. For each car, the number of mechanical breakdowns follows a Poisson distribution with a mean of 1 breakdown in 100 laps. The first car does 20 laps and the second does 40 laps. What is the probability that there will be no breakdowns, 1 breakdowns, more than 2 breakdowns altogether? Assume that breakdowns are attended and the car continues on the circuit. So there are two identical cars, right? So for each car, the number of mechanical breakdowns follows a Poisson distribution with mean 1 breakdown in 100 laps. 1 breakdown in 100 laps. So, okay. So, for 100 laps, 1 in 100 laps for each car, right? The first car does 20 laps and the second does 40 laps. What is the probability that there will be no breakdowns, 1 breakdown, more than 2 breakdowns altogether? Assume that breakdowns are attended and the car continue on the circuit. That means a breakdown එකක් වුණොත් ඒ breakdown එක හදලා ආපහු කාර් එක circuit එකට දානවා. ඒ කියන්නේ probability එක වෙනස් වෙන්නේ නැහැ කියන එක කියන්නේ, right? Probability එක වෙනස් වෙන්නේ නැහැ. ආපහු කාර් එක breakdown එක හදලා ආපහු track එකට circuit එකට දානවා. Okay? So if we consider X is the number of breakdowns in 20 laps, right? It says the first car does 20 laps. So we put the random variable X as number of breakdowns in 20 laps. And second does 40 laps. For here, for the second car, number of breakdowns in 40 laps is 5. Right? So then what is the mean of the random variable of X? So it says each car number of mechanical breakdowns follows a Poisson distribution with mean of 1 breakdowns in 100 laps. Lap 100කින් තමයි එකක් breakdown වෙන්නේ මේ දෙකම. 100කට එකක්. එතකොට 100කට එකක් නම් අපිට ඒක mean එක විදිහට පාවිච්චි කරන්න බෑ. මෙතන laps තියෙන first car එකේ 20යි, second car එකේ 40යි. So we need the mean within the given interval. අපි අර කලින් කිව්වේ week එකකට mean එක lambda නම් for 2 weeks it should be 2 lambda. For 3 weeks it should be 3 lambda. For t time period it should be t lambda. Right? So then what is the mean for 20 laps then? If it is 1 for 100, what is for 20? It is 0.2. For 100 laps, 1 breakdown. Then what about 40? It is 0.4. Right? Is it clear? So number of breakdowns in 20 laps follows a Poisson distribution with mean 0.2 and the random variable y number of breakdowns in second car in 40 laps, it follows the Poisson distribution with mean 0.4. We can't directly take the 1 over 100 or 1 breakdown in 100 laps for the distributions of X and Y, because X and Y are for it's 3:28. Do you have lectures at 3:30?
Yes, madam.
Okay, I'll hurry up then. Okay, for x follows Poisson with 0.2, y follows Poisson with 0.4. So if we take the capital T to be the total number of breakdowns, so now we define a new random variable T, that is the summation of x and y. So the problem asking is no breakdowns altogether. No breakdown altogether means what is the probability where T equals 0, right? So if we take the T as the new random variable, then what is the distribution of T? It follows the Poisson distribution with m plus n, that is 0.2 plus 0.4. It is Poisson with 0.6. Right? So now we can find these answers to these problems. No breakdowns means T equals 0. So it's same as T follows the Poisson distribution with 0.6. So what is the probability of T equals 0? So just substitute e to the power minus 0.6 into 0.6 to the power 0 and factorial 0. So it's just e to the power 0.6. Answer is 0.549. Right? And then second one is one breakdown, that is P equals T. According to the equation, you can find it. And more than 2 breakdowns, more than 2, that is T greater than 2, it can be written as 1 minus P less than or equals to 2. So P less than or equals to 2 means P T equals 0, T equals 1 and T equals 2. So finally you ended up with this answer. Right? So these are the things I wanted to discuss with you in the chapter 3, discrete probability distributions. So far we have learned 7 distributions. So it is uniform distribution, binomial, Bernoulli, binomial, geometric, negative binomial, hypergeometric, and the Poisson distribution we learned today. So in the Poisson distribution, under the Poisson distribution, we discussed two uses. First one is as an approximation to the binomial distribution, and the second one, we serve it as a probability function, as we discussed in earlier, right? So this is the end of the chapter 3. So next day, let's meet with chapter 4. If you have any questions, you can send to me so I can answer those questions in next session, right? So hope you enjoyed the session. So thank you for participating.
Thank you, madam.
Thank you, madam.
Thank you, madam.
You're welcome.
Thank you, madam.
Thank you, madam.
Thank you, madam.